Welcome to the fourth episode of BSc Bit-Sized Concepts. Here we take a closer look at big scientific ideas, not with heavy math, but with sharp clarity and deep insight. And today our topic of discussion is a very interesting concept in theoretical physics, which is called a Dirac equation. Well, we celebrated Paul Dirac's birthday few days back on the 8th of August. So let us understand first what is Dirac equation. Well, a very good definition sometimes make complex ideas simple. As you can see, that Dirac equation is a relativistic wave equation that describes the behavior of particles which has got a spin half and like the electron, and this was derived by British physicist Paul Adrian Maurice Dirac in around 1928. Most importantly, it is very much consistent with both the principles of quantum mechanics and special theory of relativity. And this was the first theory fully tested, and it accounts fully for special relativity in the context of what is called quantum mechanics. Now, if we go through the equation of the Dirac which he formulated, there are different formats of the Dirac equation. First, you can see this looks a little bit complicated. This is the original Dirac's equation, the Hamiltonian form, which he derived around 1928. Then this is the type of equation we will learn specifically. This is a shorthand because we have substituted the Planck's constant and C as 1. So we really don't need to write them. And this is what is called the Feynman slash notation, a kind of a notation which helps to make things shorter. So all in all, what we can tell is that the Dirac equation is a kind of a equation when the relativistic motion and mass operator acts on spin half particles wave function. They cancel out, that is why the right hand side is 0, and it matches nature's rule for energy, momentum, spin, and the existence of antiparticles. These antiparticles are very important, and this is the first time that it was derived. So what we can talk in simple language about this equation is that this equation is a kind of a quantum rule book for particles like electrons, which combines their motion, intrinsic spin, and the existence of antimatter, all while respecting the principles of special theory of relativity. So this is what we can find out from Dirac's equation, or rather the definition, and these are the different forms in which we can write Dirac equation. Now here what you can see is that this is the Dirac equation which we will take. As every equation has got a left hand side and right hand side, you can see we can call this left hand side is a kind of a rule book. That means it sets out the rule of spin half particles, how they will move through space-time, and it will move in a way which is very much consistent with quantum mechanics and special relativity. You might have a question why we are taking quantum mechanics and special relativity. Hold on, I'm going to answer that. Now on the right hand side you find something which is a 0. Why? Because if a wave function is a real physical free state, it must satisfy that rule exactly. We will clarify more on that. So as you can see, this I, then there is a gamma followed by a mu, and there is a partial mu. We will decipher all these things. These are the motion terms. That means what it tells is how things actually move. Then you have got a mass which is the m, and it couples with the left hand and right hand spinor parts. We will come to that also. And the right hand side is 0. So what it says actually is that for a free particle, where there are no external forces like electromagnetism, etc., the above operator must be output 0. And that means that the left hand side tells about the nature of the particles, how it moves, how it spins, etc. The right hand side, often 0 in the Dirac equation, tells that all of this happens without any kind of an external force acting on the particle. It is the particle's own intrinsic behavior which brings out all of the motion and whatever the statistics and the equations that we will soon look. So the right hand side is 0. That means it's a real physical free particle state, and it evolves out of its own nature. Now having said that, we will come now to the definition part again, and the first part of the definition brings out to this. So the left hand side 0 means the wave function evolves freely. That means there is no external force I was talking about. Without external fields, it follows the natural relativistic dynamics. Now, as I was talking, that a simple definition reveals a lot of complex ideas and makes things simple. The first thing that we would learn from this definition is what is called a relativistic wave equation. Now, what do we mean actually by relativistic wave equation? First of all, you see this definition I have highlighted and underlined that this equation is a relativistic wave equation. Now, in order to understand what is a relativistic wave equation, first we will understand what is a non-relativistic wave equation. And you're all aware about that. In classical physics, it looks something like this. So this is a nice animation which will give you a feel-good factor. So on the left-hand side, what you can see that there is a second partial derivative of u with respect to time. On the right hand side, we have got another second partial derivative with respect to space. So t mentions the time and x mentions the space, and c, as you all understand, is the speed of light. So what it tells is that if I talk of the classical wave equation, it tells that the acceleration in time of the wave at a point is proportional to the curvature of the wave at that point in space. That means overall we can say how fast a point on the wave speeds up or slows down in time. It depends on how the curve the wave is in space, and this partial differential equation actually talks about that. So what we can see from here is that a classical wave equation treats time and space differently. As you can see, we have got a t, we have got a x. Also, we find that it works fine for sounds, string waves, sound waves, but not for particles and fields. And the most important thing is that it has got no mass term. That means it applies only to massless particles or disturbances moving close or exactly at the speed of light. Now, as you can understand that Einstein, when he arrived in the scene, showed us that space and time are not separate entities but are woven together in a single four-dimensional fabric which is called a space-time, and this animation will help you to visualize more. So now the question is that, as you can see, the classical wave equation treats time differently, treats space differently, but Einstein's equations tell that fabric of space-time is one. So now the question is that if we want a wave equation, a mathematical description of how things like light, particles or quantum fields propagate that works as the universe as Einstein described it, we cannot treat space and time differently. Isn't it? We have to have an equation that must respect the fact that space and time are intertwined. And here comes the equation. It is called the Klein Gordon equation. We will come to that later. Now, this is a relativistic wave equation, first attempt, a kind of a Schrodinger equation, but in simple terms, it tells that how a relativistic quantum particle wiggles or moves in space-time. It is like Schrodinger equation, but upgraded to Einstein's relativity. So we will take this equation further, and you can see there's a box which is a little bit different from the notation. Now what this box is, we will come to that part. This is called the D'Alembertian operator, which is named after Jean-Leronde d'Alembert, a French mathematician, physicist and philosopher. This equation tells that it obeys Einstein's relativity. That means if it has no mass, the ripples always travel at the speed of light, and if it has got a mass, it still follows the principles of relativity. Now, how this equation treats space and time on equal footing, because we have to take space and time together, because otherwise it would be classical equation. We have to take something which follows the rule of relativity. Okay, so we will take this box which is called the D'Alembertian operator, and we can write something like this. Don't worry if you don't understand that, I will just make things very clear to you. Here you can see that if I take vis-a-vis the classical equation, this classical equation has got a partial square by partial t squared. What does that mean? It means that how the wave changes over time. And it has also got a paired, which is the spatial curvature time partial square upon partial x squared. Now, in order to, but here you can see that space is different, time is different. So they sit on opposite sides with different coefficients. Now, in the relativistic equation, if I take partial square by partial t square, there is still there, but it has got a scale of 1 upon c squared. Now, what do I mean by 1 upon c squared is that to add them consistently, we need them to scale by the time derivative 1 upon c squared. So both the terms have the same unit, that is 1 upon m square or meter squared or something like that. So what we have done is that space is measured in meters, time is measured in seconds. Multiplying time derivatives by 1 upon c squared converts seconds into meters in terms of wave behavior, letting space and time speak the same language. So we will go to the next part and we will take a closer look of this and things will become clear. So here you can see the classical wave equation. I have highlighted this in red. It has got no mass term. But if we take the general relativistic wave equation, the Klein Gordon equation, it has got a mass term, definitely. It has got a mass term. This m is the rest mass of the particle and c square is basically the speed of light. So what it tells is that if m equals to 0, that means it has got no mass, then the D'Alembertian operator would be 0. That means what? That means massless relativistic wave equation, same as classical form. Now suppose m is not equal to 0. That means these are called massive particles. Massive does not mean heavy. In physics we mean massive particles mean those which have got a kind of a mass. So massive relativistic wave equation allows slower than light motion. So for the first time we are moving out from the classical wave equation and we can find the mass term which is not close to the speed of light but something which has got a mass. So from here what you can see, this has only as derivatives, it says the wave's behavior entirely from how it curves in space and time. And now we have got this equation, it has derivatives but it has got a mass term that does not vanish unless m is equal to 0. So the key takeaway is that in classical waves the behavior comes purely from how the waves curves in space and time. But in relativity, the wave's own mass adds a kind of a twist, influencing its motion even when the curvature is actually 0. So we got the Klein Gordon equation, the first attempt in order to describe not only massless particles but also with mass particles. And now we will see this one, this D'Alembertian operator. You can see here this is the time part, this is the space part. So now we have got equal footing by combining them in a form which is invariant under Lorentz transformation. So what is the benefit of invariant under Lorentz transformation? That means it will be the same for all the observers. So here you can see this 1 upon c squared partial squared by partial t squared is the time part. And this one is the space part. So what we are actually doing, we are doing nothing. We are actually taking the it measures the curvature in space, how much the fields bend in all spatial directions. And you can see from here, those who can understand the Laplacian, this nabla squared is nothing. It is a space-time version of the Laplacian from classical physics. So what you can see from here is that this phi is basically a scalar field. It is a function of space-time. That means x, y, z and t. It is a 4-dimension. And what we can see from here that this waves moves through space and time in a way that obeys Einstein's relativity. That means if it has no mass, this ripples away and travels at the speed of light. But if it has a mass, it still follows relativity. So here you can see the D'Alembertian operator measures acceleration in time, how the field changes. And the second term, the nabla squared, measures curvature in space, how much the field bends in all spatial directions. So the key point is together these terms measure space-time curvature of the field in a Lorentz invariant way. Lorentz invariant way means that we get something which won't change with the change in the frames of reference. So this is really wonderful. I mean to say the relativistic wave equation taken in part, which has got an equal footing. That means time and space are equally treated. The time part is there. We have scaled by 1 upon c squared so that we can take all them in a single unit. We have replaced this with the Laplacian Nabla squared, and what we are getting is basically the partial derivative with respect to y, with respect to x, y and z. And we have got a function of space-time which is also following the fourth dimension of special theory of relativity. Now, with this kind of a relativistic wave equation, what we find is that prior to that, we have got a wonderful equation by one of the greatest mind in terms of quantum mechanics, Erwin Schrodinger. But we also find that there are certain limitations in terms of Schrodinger equation. Now, why we are trying to understand the limitations? Because based on those limitations, Paul Dirac actually explored that. So we call it a research gap, and then we try to address that research gap. So here is the limitations of Schrodinger's equation. You can see very clearly that what we find is that the time derivative is in first order and the space derivative is in second order. That means time and space has not been taken on equal footing. So m is the mass that we are talking about. Schrodinger equation treats time and space differently, whereas Klein Gordon equation is the first step of a relativistic equation, and here you can see the time is also second order derivative and the space is also a second order derivative. So from here you can see this appears side by side, and this pair is exactly the Lorentz invariant wave operator. So getting a Lorentz invariant wave operator makes things simpler. We get something on equal footing of space and time following special relativity, and something which doesn't change with the change in the frame of reference. So if you take the other version of this Schrodinger equation, the mass m refers to the rest mass over here. So the particle has mass greater than 0. The particle moves much slower than the speed of light. I mean to say, these are the limitation. It is very good for slow particles. At higher speeds, the Schrodinger equation gives wrong predictions. So speeds v less than equal to c, it works out. Like photons m equal to 0, it doesn't work out. And remember, the Schrodinger equation is a classical. It is a classical equation. It is just the classical kinetic plus potential energy. Whereas on the other hand, when we go to the Klein Gordon equation, we find that yes, if there is a mass which is greater than or equal to 0, relativistic speeds are allowed. Derivative is from relativistic energy momentum relation, and both of them take the same derivatives, that is second order, both in terms of time and space. So this is the Schrodinger's equation limitation in terms of things which are closer, or a mass which is the rest mass, and it was not following and giving correct equation if it is traveling close to the speed of light, etc. So here now let us take a comparative look so that we understand the two limitations and two equations, and then go for the Dirac equation. So here you can see that this is the Schrodinger equation. So what we see, massive particles, well, m is greater than 0, non-relativistic v is less than equal to 0, and it has got a built-in spin, but the spin is not being accounted, and it is based on the classical kinetic energy. If we go to Klein Gordon equation, we find yes, where m is greater than equal to 0, relativistic speeds are allowed. It takes into account only the spin 0. We will come to the spin part, and it is derived from the relativistic energy, and the wave function is a scalar field. And now comes the master stroke of Dirac equation, where the massive particles, it can handle both m greater than 0 and m equal to 0. It has got relativistic speed, and it deals with spinhalfparticles. It is directly included, the spin, and it is first order in both time and space, and most importantly, it predicts antimatter very naturally. So this is a kind of a comparative understanding of Schrodinger equation, the first classical equation for which Erwin Schrodinger received the Nobel Prize in physics. Klein Gordon equation, first attempt for a relativistic wave equation. There were limitations, and the final master stroke of Paul Dirac, which actually solved everything. Now, as we go ahead in understanding Dirac equation, another important thing which comes across is called a spinhalfparticle. Now this is very important because all the classical quantum equations or Schrodinger equation, etc., they never dealt with something which is called a spinhalfparticle. So here you can see again I am revisiting the definition, and I am telling that it describes the spinhalfparticles. Now here comes a very important note. Despite the word which is called spin, electrons are not tiny balls physically rotating around an axis. So instead, spin is basically an intrinsic quantum property, something built in the very nature of the particle, like electric charge or mass. So don't think that it is just like a spinning top, it is spinning. No, you cannot stop or speed up a spin. It is fixed of a given type of a particle. Now, you might have a question, then what does spin tell about? Because if it is inbuilt, then definitely it has got certain things. Yes, it has got some very important phenomena in terms of understanding our standard model. First of all is that spin tells how a particle behaves under rotation. That means if it is spin 0, no change at all, it looks identical from every angle. Spin half, we will come to that. Wave function changes sign after 360 degrees rotation. Spin 1 returns after 360 degrees but has more possible orientation. So the particle, how it behaves, is being guided by spin. Again, a quick note, spin does not mean a spinning top. It is an intrinsic property. Spin also tells us whether a particle is a fermion or boson. Definitely it is very important, because half integer spin are fermion, that means they obey the Pauli exclusion principle. Integer spin boson, this is the Bose-Einstein statistics, can occupy the same state. Further, you will see that spin controls whether a particle is fermion or boson. That means spin 0, it is only one state. Spin half, spin up or spin down. Spin 1, either spin -1, 0 or +1. It also tells about the spin quantum numbers. Spin 1 particles are, for example, W plus and W minus and Z and gluons and so on. So overall, what we can tell is that spin tells us how the particle's wave function behaves when rotated. Again, rotation does not mean the rotation that we will talk about. How many spin states it can have, whether it is fermion or boson, and many other important features. So this is actually what spin actually talks about. So remember that examples of spin half particles are electron, proton and so on, and massive particles actually means can move slower than speed of light. Massive particle does not mean 10 kg or 12 kgs. And when we say spin half particles can be massive, that means they can have a non-zero rest mass, unlike photons which are spin 1 and they are massless. Now here comes the very important, the master's stroke of Paul Dirac is that measuring the spin half particles was not an easy task. And measuring the spin half particle was not done by Erwin Schrodinger or the classical wave equation. In order to do that, we need to understand a very important but a tricky concept in particle physics or theoretical physics. What is a spinor? Now, spinor is something which is very counterintuitive, and this is very important in understanding Dirac equation. Now, what happens actually with spin half particles? Now, let us imagine that when you rotate your body in 360 degrees rotation, what it happens is that it comes back to the original state. But in case of spin half particles, it does not. So, for example, here is your arms extended 0 degrees, you move 90 degrees, then you move 180 degrees, then obviously in 360 degrees you come back. But in order to make an electron rotate, electron does not come back at 360 degrees. It comes back but with a negative sign. That means imagine that you have got this wire, your mobile wire. So if you're making one 90-degree rotation and then another 360 degrees rotation, it is not coming back. It is further twisted. So you have to again twist it and again twist it. So only after a 720 degrees rotation, your cable wire or your mobile charger is being unwired, or it will unwind yourself, and it will be it will come out of that tangled state. And this happens exactly with an electron. So for an electron, if you rotate by 360 degrees, here you can see I am using the bra and the cat notation. It is minus. But when you rotate 720 degrees, it becomes positive. So in order to interpret that, Dirac has to introduce a new concept which is called a spinor. So spinor looks like this: psi 1, psi 2, psi 3 and psi 4. So psi 1 and psi 2 are amplitude for particles spin up and spin down, and you see the bottom part, it actually shows the antiparticles which spin up and spin down. So we can say, we can divide further this psi into two parts. Let us say a phi and a chi. So this phi actually tells that it holds amplitudes for positive energy states, and this chi actually tells what is the negative energy states. And for the first time in the history of physics, we got an understanding of negative energy states. History tells that when Paul Dirac invented this, he thought that his equations are wrong. And later, when experiment proved that yes, negative energy states or antiparticles exist, he found out that his theory was profound and it is correct. So in order to get a kind of a physical interpretation, I would say imagine a kind of analogy that you can see. This is a drawer, and the top drawer is got the phi. So it has got a spin up, which has got two folders, and a spin down. So this one is a particle spin up and this one is a particle spin down. And the bottom drawer, which is a chi, it has also got a spin up and a spin down, this one and this one. So each drawer has got two folders. The first one, which is particle spin up and spin down, and the bottom one has got an anti-particle spin up and an anti-particle spin down. So when the mass comes into existence, these drawers exchange the files. So remember, the diracspinor was the first mathematical object to automatically include spin as a consequence of relativity, not an extra assumption. So it also predicted antiparticles, which you can see the bottom drawer, which no one had ever seen yet. A few years later, when the positron was discovered, Dirac's second drawer was found to be real. So this is the concept of spinor. But remember that spinor can be extended to many other things. There are concepts called chirality, etc., which I have not included because this is bit-sized concept, BSc. So I'm trying to keep it as simple and as clear as possible. So we are done with the second part of the definition. What is a spinor? Now the definition also tells that this equation is consistent with special relativity and quantum mechanics. Now what on earth that we will bring up suddenly special relativity and quantum mechanics? Let us understand that. Now before Einstein and Schrodinger, physics was built on the foundation laid by Isaac Newton. So Newton's law, as you can see, of motions and universal gravitational law could describe everything from a falling apple to the orbit of planets, and the second law connects force, mass, acceleration and everything. Now in Newton's world, space and time are absolute. Clock ticks the same for everyone. No matter where they are and how they are moving fast, velocities simply add, and there is a fundamental speed. There is no fundamental speed limit, and this works with everyday motion. But as we push ourselves close to the speed of light, as you can see in the atomic scale, Newton's law starts to break down. There are limitations, and that is when another person comes in, and that is this person, Albert Einstein. So on the left hand side you can see we have Einstein studying at Princeton, whose relativity connects with space, time and energy. The equations that describe the gravity is a curvature of space time. We have got special relativity, which rules the very things which are fast. So we have Schrodinger, on one of the founders of quantum mechanics, as you can see right on the screen, who gave us the equations that describe the behavior of particles at the microscopic level. Instead of definite position and velocities, we have possibilities and wave functions and whatnot. So all what we can find is that we need to unite what is called the very fast with the very small. So anything which is moving very fast have to obey Einstein's special relativity. Anything which is moving at a very small scale have to obey the rules of quantum mechanics. And that is why you see that Schrodinger's equation come in play as the first attempt for I would say a wave equation, but non-relativistic. So from here what we can say that if we try to understand how subatomic particles move, we have to go for quantum mechanics, and if you have to find out how things move at a very high speed, then we have to go for special relativity. Hence we need to marry these two frontiers, special relativity with quantum mechanics, and we get what is called a relativistic quantum mechanics, or rather which we are now trying to see is that quantum field theory. So this actually tells you why we need to find out an equation which is consistent with special relativity and quantum mechanics. And now we have come to the final part of our video, that we will decode the Dirac equation. We will find out in a very easy way what are the components of this Dirac equation all about. Now first we see there is an I, and we all know what is I. So in the Dirac equation, actually I ensures that the wave function evolve in a way that keeps probability conserved. And when I say probability conserved, what do I mean? If we add up the probability, it must always be equal to 1. So mathematically, if I take this one and I square it, that means I take the probability density, it must stay the same for all t, if I add up all the space. So from here, what we can say, that if we don't have an I, then the solutions become really uncontrollable. That means we might get a real exponential, and for a real exponential we might get a growth or a decay. And if you remove I from Dirac equation, this creates a problem. So it is a kind of a thing that the probability amplitude would either blow up if the exponent is positive, or it will fade away to 0 if the exponential is negative. So all in all, what we can say is that if we remove, it is just like replacing this with this. So from here, what we can say is that I actually ensures a stable oscillatory behavior instead of a runaway or vanishing solutions. So the core reason quantum particle can persist without, I would say, violating the probability. So if I is not there, we would have got something else. That means spontaneously things would vanish or appear from nowhere, violating quantum physics. So I in the Dirac equation ensures that probability is conserved and we are not getting a real exponential, otherwise the equation will blow out. The next factor which we see, you're all aware about, not much to mention. It is called the reduced Planck's constant, without which the things will be classical. The next important part is a very important and a very interesting part, which is called this gamma mu. Now note that this mu is right on the top. Can you understand what do I mean by that? Okay, well, I will explain to you. So gamma mu are basically what are called gamma matrices, and these are basically a special set of 4x4 matrices that acts like the direction of space-time for particles with spin half. Now, if you have gone through my Einstein field equation, we have got a mu. So the concept is the same. 0 is the time direction, 1, 2 and 3 are the spatial directions. Something like this. So what it tells, very simple. The index mu tells which direction in space-time the matrix is associated. For example, in relativity, we write A mu. For a 4 vector, we write gamma mu. So it is a matrix valued 4 vector. Remember, it is not a vector for numbers, but a vector for matrices. So that actually tells you what it is. So think of gamma matrices as a set of directions in space-time. But instead of being just numbers like x, y, z and t, each direction actually represented by a matrix. These matrices are as designed so that when you combine them, they reproduce the space-time geometry in a matrix form. Now here you see that this gamma matrices, if I write it in a detailed manner, so this is the time component, space component, space component, space component. So you have got 0, 1, 2 and 3, and this together, all of them make the gamma matrices mu. Now remember, I have got the index mu right on the top. So those who know tensor, you are already aware this is nothing but a contravariant space-time indices. And what does that mean? It means that if we transform like a contravariant 4 vector, we again get the Lorentz invariant. So in this equation, you can see the gamma mu is a contravariant index and the del mu is a covariant. We will come to that. This is the master stroke of Dirac and you will be astounded to find that. So what it tells is that to contract indices properly in relativity, the other factor gamma mu must have an index up. That means it has also got an index down. So that is the del mu. I will come to that part. So together when we contract is using the Einstein summation convention, you get a Lorentz scalar operator. That means it is same for all inertial frames of reference. So the key takeaway is that the gamma matrices are special 4x4 matrices that represent the time and space parts of space-time in the Dirac equation, and when combined with derivatives which were coming, the del mu, they form a Lorentz invariant operator, and this is same for all inertial frames of reference. Now here you see a very important note which is important to mention. The contravariant or covariant, when I'm mentioning, refers only to space-time index, okay, and not the nature of the matrix. Let me tell you what do I mean by that. What I'm trying to tell you is that space-time index mu, this is simple a Minkowski space index. As you can see, it is a flat space-time 0, 1, 0, 1, 0, minus 1. And it is a contravariant, means that when you perform a kind of a Lorentz transformation, a boost or rotation, whatever, the mu transforms like an index of 4 vector. But remember, regardless of whether the index is up and down, the matrix structure is not the same as space-time index. That means the matrix structure lives in a spinor space, which we have just seen. And it has its own Lorentz transformation rule. But the space-time index, contravariant and covariant, is something which when you get a Lorentz boost, it transforms accordingly. So the bottom line is that space-time index follows the contravariant covariant rules and matrix part follows the spinor transformation. So it is a reminder that you should avoid mixing up these two worlds. Space-time index follows the contravariant covariant rules of special relativity, and matrix part follows spinor transformation rules, which are different and unrelated to covariant and contravariant tensor rules. So here is the final summation. The gamma matrices gamma mu are matrix valued 4 vectors, but the index mu is contravariant in the space-time. But the object itself lives in spinor space and acts on spinor. So remember, they are not ordinary tensors or numbers, but operators whose space-time index transforms like vector. So this is quite important. Now we will come to the next important. So gamma mu is basically what is called a contravariant index. Now we come to the very important, interesting, the partial mu. So the partial mu is nothing, again 0, 1, 2, 3 as usual, but instead of having space-time derivatives separately, we wrap them into one partial derivative, that is partial mu. So as you can understand, then in special relativity, space-time are a 4-dimensional object. So instead of having del upon del x, space in x direction, del upon del t, time in this direction, we bundle them up as this. And you can understand that we can very well make them in a Laplacian operator. And that Laplacian operator is further generalized as a D'Alembertian operator, which I have showed earlier. So here is the normal 3D space. You can see the Laplacian, the nabla f. But when we add a little bit of partial by partial ct, this is the time part. It also includes the time derivative, and it works in space-time. Just instead of space, now it works with space-time. So this is how the partial mu means. This is the space part, and space part, instead of putting all separate, we have bundled them up, so make things easier. So this is the natural relativistic derivative. So here you can see, you can also think that if you switch frames, for example frame reference A to frame reference A prime, and if you reshuffle them, okay, the components remains the same. The components of the space-time in inverse manner, so the derivatives of scalars remain scalars. I will come to this part. What do I mean? So here you can see partial mu, this it transforms as a covariant vector. Gamma mu transforms like a contravariant vector of matrices, and when you contract them, you get this. So the transformation effect cancels out and the equations look identical. What I was talking about, Lorentz invariant factor. And let us look this wonderful thing in a very quick example. Now suppose you have got two numbers A and B, and these numbers are in a frame of reference. You multiplied them, P equals to A times B. Now suppose you have another frame of reference. I have mentioned them stretching, you can do it for rotation, etc. And here the new rule is that B gets multiplied, or rather B prime gets multiplied as KB, and B gets multiplied like this, and A is changed in the opposite direction. That means A prime is equal to A upon K. Now the question is that what happens to P? Now if you just do the simple algebra, you will see here, if I substitute A prime, what is A prime? A upon K. What is B prime? If we just put it as B, so A prime, A upon K times KB, the KK cancels out, and A times B equals to P. So what actually it shows that the P remains invariant. So if you go back now to this previous part, here you can see what this gamma mu is actually doing. The gamma mu, when it is coupled with partial mu, both of them are cancelling out. That means this Lorentz invariant is producing a number just like this analogy, that P remains the same. So you won't have to worry that what will happen in this frame of reference or that frame of reference. So what you can think of this, B you can think of as partial mu, changes under one way. A is the gamma mu, changes in the reverse way. So reverse way and this way it cancelled out and P remains the same. So that is what covariant means here. The individual parts change, but they change in exactly opposite direction. So the whole combination is the same for all observers, and we have achieved our target, that is the Lorentz invariant factor. So here you can see the 4 gradient partial mu is called covariant because it transforms along with space-time. If you change the frame of reference, the Dirac equation still has the same form. It is like different people using different coordinates, but the actual rate of change they measure is the same physical thing. So this is what is called the Lorentz covariant factor, which is achieved using a covariant and a contravariant indices. Now we come to the very familiar, I don't have to explain much, that is the M, the mass. If M is not equals to 0, we describe massive fermions. If M equals to 0, it is massless fermions like an idealized neutrino. And C is obviously the speed of light, we set it to 1. Now the next thing that we got here, I have already explained, this is called a Dirac spinor. We have already explained that. It is a wave function of a relativistic spin-up-particle. It has got 2 parts. This one describes the particle spin up and down, and this is the anti-particle spin up and down. But there is a very important quick note in terms of explaining this spinor. Now Dirac spinor, remember, is a wave function, but it is not the same in Schrodinger's equation. Now in Schrodinger equation, as you can see, what we get is something like this. It is just a single complex valued function, which means that at every point or position x and every point in time, the wave function assigns a single complex number. I mean to say the Schrodinger equation. So this number, what does it contain? Both amplitude and the phase information of that particular wave. But here you can see in Dirac equation, it is not the same. At each point in space-time, you have a 4-component complex column vector, which is basically the spinor. So the difference is that in terms of Schrodinger equation, you get a complex number which denotes every position x and every time t, and it assigns a single complex value. But in case of Dirac equation, this is c to the power 4. That means you have a 4-component complex column vector, and that in short we can say about this is that in quantum mechanics, a wave function is just a mathematical object, but in Dirac spinor, it is representing a relativistic spin-half state. So the difference is that Schrodinger is a scalar wave function and Dirac gives us multi-component spinor wave function. Having said that, we come to the last part of our video, that what is actually the significance? Why do we at all care about Dirac equation? Definitely it carries a huge amount of importance. The first thing that we get is that it unifies quantum mechanics with special relativity, making the equation valid for particles moving close to the speed of light. Next, what we get is that spin, the concept of spin-half particle, arises directly from the mathematics, not as an added assumption. Next, what we get is that it explains both electrons, massive, and neutrinos, massless, in certain formulations. It explains what is called the magnetic moment. It predicts the intrinsic magnetic moment. Also, what we see that it can describe both electrons, massive, and neutrinos, massless, in certain formulations. It is the first which predicted what is called the antimatter. It also has a very important part which I have skipped, which it is very technical and will take time, which is called chirality. It distinguishes left-handedness and right-handedness components essentially in weak interactions. And finally, what we can see that it actually gave the foundation. It actually is a stepping stone for describing particles' creation and annihilation and the interaction in modern physics, which led to what is called the quantum field theory. So that's all in our bit-sized concepts. I have given a fairly detailed ideas starting from the reason, the understanding, the each and every component, the concepts of spinor, etc. So thank you very much for taking your time and watching this video. If you like, please do not forget to subscribe to my channel Physics for Students and click on this bell icon so that you get all the notification from Physics for Students. You can further follow me on my social media handles, and you can write me to this email ID for any further clarification. I respond to the emails as early as I can. Physics for Students will continue with this bit-sized concepts and the long courses which I have started. We'll see you soon, very soon. But till then, may the good Lord be with you.